In organic chemistry, resonance is the movement of electrons between atoms in a molecule. Now, this can happen for many different reasons, and I'm going to try to give you a list of the possible scenarios in which resonance can happen. Now, one thing to keep in mind is that the atoms doing resonance have to be sp2 hybridized, and that's because they're moving pi electrons. And so, let's just look at the first scenario. Here we have a negative charge on this carbon atom over here, and we have the other atoms over here have pi electrons in a pi bond. And so this negative charge can actually move from being a lone pair to being a pi bond with the carbon next to it. But in order to make sure that this carbon does not break the octet with its 5 bonds, because remember this actually has a hydrogen on it, it's going to move its pi electrons over here from a pi bond into a lone pair on the carbon atom next to it. And so we get this possible scenario where we have a double bond here, a double bond here, and actually a negative charge over here. And this can move again to form a pi bond with the carbon atom next to it, and this pi electron over here, the pi electrons over here can become a lone pair on the carbon next to it. And we get this possible scenario where we have a double bond here, and negative charge over here. And then this obviously can move and become our original structure over here, and they keep interchanging, so it's not one structure or the other, it's actually a mix. Now that's with the negative charge. Now what if you have a positive charge? Now this carbon, it's not going to move a positive charge. Positive charge means you have no pi electrons over here. But what oxygen can do is actually donate one of its lone pairs over here to form a pi bond with carbon, and this will give us the R group that we have, the carbon, its hydrogen, and now carbon has a double bond over here with oxygen, and oxygen has a single bond here to hydrogen. Now the positive charge is now on oxygen actually, because now oxygen has 5 electrons surrounding it instead of 6, which would give us a positive formal charge. And this is the 1, 2, 3, 4, 5, just for evidence. And so this actually makes this oxygen really acidic, in fact. And so this is one of the resonance structures of this molecule. Now, when we have a radical is not a pair of electrons, but only one electron. And so you have to make sure that we're actually using half arrows when we're showing the movement. And so if this were to try and form a pi bond, here's the half arrow, we need another electron to move over here. And so that would give us the full pair. Now this electron over here, that's now going to be marked in red, is going to remain on this carbon atom. And so what we end up getting is now benzene, right? Or methylbenzene at least. Now a double bond over here, and we have our double bond over here, a double bond over here, and now a radical that's on this. And this is going to keep moving back and forth between the different atoms by moving with this half arrow, one of these electrons moving here with this half arrow, and the final electron becoming a radical, and so on and so forth. And so we actually end up getting 4 structures over here, if I'm not wrong. Double bond over here, double bond over here. Then our radical will be here. So let's mark it in red. And one will be here. And then we can show our double bonds as they are. And so these are your resonance structures for benzene when you have a radical. Now, some of the other scenarios in which we have resonance is when you have a molecule that's actually not charged. And how do you get resonance in a molecule that's not charged? Well, as long as you have your pi electrons and they're sp2 hybridized, you can do it. Now, you're looking at this nitrogen. It has 1 sigma bond, 2 sigma bonds over here, and a third one to the other hydrogen, and then a lone pair. So that's sp3 hybridized. But in fact, it can actually donate that lone pair over here and form a pi bond with carbon, and carbon moves that pi bond with oxygen and becomes a lone pair. You get an R group, carbon, oxygen with a negative charge because it has 3 lone pairs around it, and then a double bond with nitrogen, and there's 2 hydrogens, and that gives it a positive charge. So actually this nitrogen is sp2 hybridized, but it's just secretly sp2 hybridized because of this resonance form. Now with ozone, this molecule is also not charged, but there is a separation of charge within the atoms. If we draw it out, we have 3 oxygen atoms. In fact, we have a double bond here and a single bond here. And then we have our 2 lone pairs over here, 1 lone pair over here, and 3 lone pairs over here, and then 2 lone pairs over here. So let's draw that better. And so what that means is that for this oxygen atom, we have a negative charge. For this one, we have a positive charge, and here we have a neutral charge. And so there's separation of charges, but overall the atom is 0 charged. And so this can resonate in between back and forth with the other resonance form where we have an oxygen over here. When we have one of these electrons go over here, and then one of these pair of electrons go over here. And so we have this. So our negative charge would now be on this atom. Positive charge is still on this atom, and that's because of where the pi electrons are at. And so it's not one structure or the other, but rather a mix. And so those are the 5 different scenarios in which you can have resonance. One with a negative charge, a positive charge, a radical, and no charge.